So we talked about IR, hydrogen NMR, and carbon NMR. Now we are going to use these techniques that we learned about to determine the structure of molecules. So in order to do that, there are 4 steps that we need to follow. So in most of the spectroscopy problems, the molecular formula is given. So the first step is to calculate degrees of unsaturation, or HDI. That gives us information about whether we have a double bond or a ring or a triple bond or none of them, which is very important to know about the structure. Also, if you consider these type of problems as a puzzle, we need to analyze what pieces of puzzle we have, and that can happen by looking at IR or NMR spectra. So IR can tell you what type of functional groups you should have in the structure. For example, if you see a smooth broad signal at around 3500, you can think about presence of an alcohol. Or if you have a sharp signal at 1720, it can be a ketone, or at higher wave numbers such as 1740, it can be an ester. So after finding this information, then you need to look at the NMR. So for example, in hydrogen NMR, you need to consider the number of signals. If you have 8 hydrogens in the molecular formula and you see 2 signals, so you can expect to see some sort of symmetry in the molecule. Then you need to analyze each signal, their chemical shifts, integration, and multiplicity, and think about the pieces to complete your puzzle. Now let's look at the first example. So here we have the molecular formula of C6H14. So the molecular formula is given. Now when you see the molecular formula, the first thing is to calculate HDI. We also have the carbon NMR, and in carbon NMR we have 1, 2, 3 signals. However, if you look at the formula, we have 6 carbon in the formula. So we should think of some sort of symmetry in the molecule. Now let's calculate HDI first. So the HDI for this molecular formula is 0. Now that means we don't have any double bond, a ring, or triple bonds in the molecule, so we just have all single bonds. Now how can we connect 6 carbons to one another with just single bonds? So we can do it in different ways. I can have something like this, or this structure, or this one. So I'm going to draw all the constitutional isomers for C6H14, and that's gonna give me all of these structures. So 5 structures can be drawn for C6H14 with HDI equals to 0. Now let's see how many signals each of these structures can give me. So looking at the bottom structure, so we don't have any symmetry in this molecule. These methyls are identical, so they are connected to the same carbon, and we have a single bond, so we have free rotation here. Therefore overall we are going to see signal for this, and this carbon. So overall 4 signals here. Now in this structure we have 2 plane of symmetries, one right here and one right here, and that cause to see a signal for this carbon and this carbon. So 2 signals here. Now looking at the third molecule, we have a plane of symmetry here. So that means I'm going to see a signal for this one, for this one. This carbon is exact the same as this one, and this methyl is exact the same as this one. So overall 4 signals here as well. Now let's look at this structure. So we don't have any plane of symmetry here. These two methyls are just identical. So we are going to see 1, 2, 3, 4, and 5 signals here. Now in the first structure, so we have some sort of plane of symmetry here. So basically this methyl is exactly the same as this one. They have the same chemical environment. Both of them are connected to CH2 groups. These two CH2 groups are exactly the same. Both of them are connected to methyl and another CH2, and these two CH2s are exactly the same. So we have some sort of plane of symmetry here. So we are going to see 1, 2, 3 signals for this structure. Now looking at the carbon NMR, we just see 3 signals, and that matches this structure. So that could be the structure for C6H14 and this carbon spectrum. So in this practice problem, we are given hydrogen NMR, IR, and carbon NMR. Carbon tells us that we have 3 peaks for this structure. The molecular formula is also given, so we can calculate HDI. Now, before working on this question, something about hydrogen NMR I would like to mention is that this subsection here at around 12 ppm is part of the spectrum. So what happens is that in a lot of NMR spectrum, if we see a peak all the way at higher ppm, and if there is nothing after, for example, 2.5 to 11.5 ppm, this part of the spectrum is cut out, so we can see these signals more clearly. But this is just one spectrum, and that subsection is part of the spectrum. So we have a peak at 12 ppm for this structure. Now let's work on this problem. So the first step is to calculate HDI. And HDI for this molecular formula is 1. So that HDI equals 1 tells us that we should have a double bond or ring in the structure. Then we need to look at the IR and NMR and find out the pieces. So if you look at the IR, we see a broad signal somewhere between 2200 to 3600, right? And we also have a signal at around 1716. So both of them together can tell us that we should have a carboxylic acid functional group in the structure. So we are going to write down this piece of information. So we have broad signal at around 2200 to 35, and also we have signal at around 1716. So both of them together can tell us that we can have carboxylic acid functional group. So if you look at the carboxylic acid functional group, we have CO double bond. So that HDI equals to 1 can be because of CO double bond. So that tells us we don't have a ring in this structure. So the structure should be linear. Now, if you look at the hydrogen NMR at 12 ppm, we see a singlet with integration of 1. So this is 1 hydrogen at 12 ppm. And if you remember from the chemical shifts, that belongs to the hydrogen in carboxylic acid. So we can write it down as well. So from hydrogen NMR, we can confirm presence of carboxylic acid functional group. At 12 ppm, we have 1 hydrogen integration of 1, and we see a singlet that belongs to this hydrogen in carboxylic acid. Now, if you look at the rest of hydrogen NMR, have you noticed the splitting pattern here? So we have a triplet, integration of 3 hydrogen. So we have a triplet, integration of 3 hydrogen, and we have a quartet with integration of 2 hydrogen. So this pattern, we already talked about it, tells us that we have ethyl functional group in the molecule. Now, if you again look at the formula is C3H6O2. So we found these pieces. We have 3 carbons. So let's put all the pieces together so we can come up with this structure. Okay. Now, let's label all the hydrogens. So these are hydrogen A, hydrogen B's, and hydrogen C. Now we can also classify our proton peaks, and you might be asked to do so in the exam. So all the protons are labeled. Let's start with proton C. So we already talked about it. This is the carboxylic acid proton, and it appears at around 12 ppm with integration of 1 hydrogen. So this is hydrogen C. Now if you look at CH3, so CH3 is connected to CH2. It's an alkane, and we expect to see that somewhere between 0.9 to 1.7 ppm. If you look at the neighboring hydrogens, so we have 2 hydrogens. The multiplicity for CH3 should be 2 plus 1. So we should see a triplet with integration of 3. Now all of these information can be written here. So it's a triplet with integration of 3 at around 1.1 ppm. So that is actually hydrogen A. Now for hydrogen B, so hydrogen B is connected to the carbon, which is connected to carbonyl, and we expect to see that somewhere between 1.5 to 2.5 ppm, and it actually appears at around 2.4 ppm. So about the multiplicity, this hydrogen is connected to the carbon, and on a neighboring carbon we have 3 hydrogens. So 3 plus 1, the peak for this one should be a quartet. So let's write this down. So we expect to see a quartet with integration of 2 hydrogens at 2.4 ppm. So this is hydrogen B. Now in the next practice problem, we have this molecular formula, and we have the hydrogen NMR. So in the hydrogen NMR, we have one singlet at around 7 ppm, which is the aromatic region, with integration of 4 hydrogen. Now let's calculate HDI first. So the HDI for this molecular formula is 4. Now whenever you have HDI equals to 4, in the back of your mind you should recognize it as a benzene ring. It doesn't have to be the benzene ring, but majority of the time it is the case. So the benzene ring has this structure. Okay, so benzene has 1 ring and 3 pi bonds, so it can fit the HDI equals to 4. Now, to confirm that we have a benzene ring, you can look at the hydrogen NMR. So at around 7 ppm, as I mentioned, this is the aromatic region, which is hydrogens connected to the benzene ring. So that can basically confirm that we have benzene. Now, by drawing a benzene ring, I used all the 6 carbons in the molecular formula. Now, if you look at this singlet here, it is integrated to 4 hydrogens, not 6 hydrogens, meaning that 2 of these hydrogens should be replaced by the substituent. So if you remember previously, we talked about monosubstituted ring, and monosubstituted ring had the integration equals to 5. Now that we have integration equals to 4, we should have di-substituted ring, meaning that 2 of these hydrogens should be replaced. By what? By bromine. So we have 2 bromines in the molecular formula, therefore 2 bromines can be our substituent. So we have 2 bromines, they are our substituent. And this integration equals to 4 hydrogen at around 7 ppm tells us that we have di-substituted benzene ring. Now I get back to my question. So which 2 hydrogens should be replaced? These 2, or these 2? Now let's draw all the options. So if I replace these 2 with bromine, I'm gonna have this structure. So if I replace these 2, I'm gonna have this structure. And if I replace these 2, I'm gonna have this structure. Now, which one matches these hydrogen NMR spectrum? So let's see how many signals can we get for each of these compounds in hydrogen NMR. Now, looking at this structure, we have symmetry right here, and that symmetry makes these 2 hydrogens be the same. So we are going to see one signal for these with integration of 2, and these 2 hydrogens will be the same. So we are going to see another signal for them with integration of 2. So overall, we expect to see 2 signals for this structure. Now let's look at this structure. So we have a symmetry right here. Okay, so we are going to see one signal for this one and one signal for this hydrogen. Now these 2 hydrogens are exact the same. So we expect to see 3 signals here. Now how about the last one? So we have symmetry here and we have symmetry here. Okay, so these two hydrogens should be the same, these two are the same, so basically all of these 4 hydrogens are the same. So we are going to see one signal for all of these. So one signal with integration of 4. That means this is the correct structure for this question that matches the hydrogen NMR that we have. So let me draw the correct structure right here. So this is going to be the structure for this hydrogen NMR. So in the next example, we have molecular formula IR and hydrogen NMR. So the hydrogen NMR is plotted on a graph paper. This type of plotting was very common in the past and with old instruments, but we can use the graph paper to find the number of integration for each signal. So each of these squares or section or unit can be considered as a 1. So if you look at this signal, the step curve starts from here and ends here, so it includes 1 unit, so we can say the integration here can be 1. So we can have integration of 1 here. And for this signal, the step curve starts from here, so we have 1, 2, 3, 4, 5, and 6 units. So it can be integrated as 6 hydrogens. Okay, so let's look at the molecular formula and calculate the HDI for that. So the HDI here would be 0, meaning that we don't have any double bond, a ring, or triple bond in this structure. Now if you look at the molecular formula, we have an oxygen here, and if you look at the IR, we don't see any CO double bond at around 1720. We don't even see any broad signals at around 2200 to 3500 for alcohol or carboxylic acid. So that means we have an oxygen in the structure, but the functional group present in the molecule shouldn't be an alcohol, a carboxylic acid, or a ketone. Now let's look at the hydrogen NMR. So in the hydrogen NMR, we see 2 signals. However, we have 14 hydrogens in the molecular formula. That means we should look for some sort of symmetry in the molecule. Also, if we add up these integration, we are going to have 7 hydrogens. And if we compare with the molecular formula, we are short in the number of hydrogens on the signal. So what we can do, we can multiply each of these numbers by 2. So that gives me 2 hydrogens, and this one gives me 12 hydrogens. Now if I add them together, we are going to have 14 hydrogens, which matches the molecular formula. Now let's look at each signal and see what sort of information we can get from each of these. So this signal right here is a septet. That means we should have 6 equivalent hydrogens on its neighboring carbon. And the only way that we can have that is by having 2 CH3 groups connected to the same carbon. So we can think about having this piece in the structure. So this hydrogen is connected to the carbon, and on its neighboring carbon, it has 6 equivalent hydrogens. So 6 plus 1 is 7. So this one should be a septet, which is right here. Now, if you look at the hydrogen right here, actually we can do for one of the hydrogens, but it will be true for all of these 6 hydrogens because they are equivalent. Now for this hydrogen is connected to this carbon. Now on its neighboring carbon, it has 1 hydrogen. So 1 plus 1, these hydrogens should be doublet in the hydrogen NMR. And here we can see a good doublet at around 1.3 ppm. Now, since we have symmetry in the structure, we can think about having 2 of these pieces in the structure. So we can have 2 of these in the structure, so we can get the appropriate integration. Now, these 2 hydrogens are exactly the same, so we are going to see a signal for them right here with integration of 2 hydrogens. And these 4 methyl groups are exactly the same, so we are going to see a signal for them at around 1.3 ppm with integration of 12 hydrogens. Now, if you look at the chemical shift for this signal, it appears further downfield. So this region, if you remember, belongs to the hydrogen that is connected to the carbon, and the carbon is connected to an electronegative atom. Now we have an oxygen in the molecular formula. We know this signal belongs to these 2 groups. So what we can think of is to connect these 2 groups to one another with the oxygen in the middle. So we can have this structure. Now, as I mentioned, we have a symmetry in the molecule right here. So this symmetry makes these 2 groups to be exactly the same, and all of these methyl groups are the same. So let's label all the protons. Okay, so they are the same, and all of the methyls are the same. So the signal for the hydrogen A appears at around 3.7 ppm due to the presence of oxygen connected to the carbon, and we see a septet because we have 6 equivalent hydrogens next to it, so 6 plus 1, it should be a septet, and we see integration of 2 because we have 2 of these in the structure. So that should be hydrogen A. And for methyl groups, these hydrogens, so they are alkane first of all, so we expect to see them somewhere between 0.9 to 1.7 ppm, and actually there is a signal here at around 1.3 ppm. We expect to see them as a doublet because they have 1 hydrogen next to them. 1 plus 1 is a doublet, and we have 4 of these, so integration of 12 hydrogens. This is hydrogen B. Now let's look at next practice problem. So here we have IR, hydrogen NMR, and carbon-13 NMR. So the molecular formula is also written here. Now let's calculate HDI. So HDI will be 4. So when we see 4 or above 4 for HDI, we can always think about aromatic ring in the molecule. And as soon as you see a signal in the aromatic region in hydrogen NMR, so this region is about 6.5 to 8.5 ppm, you can almost guarantee that it's an aromatic ring. So let's draw the ring. Now, if you look at the integration for the aromatic hydrogens here, the integration is 5. And we previously talked about it. So whenever we have 5 hydrogens in the aromatic region, we should always think about having a mono-substituted aromatic ring, meaning that we have 5 hydrogens connected to the ring and the last one is substituted by a substituent. So let's draw all the hydrogens. And here we should have an attachment, and by looking at this region we can figure out the structure of attachment here. Now if you look at the carbon NMR, so carbon NMR tells us how many different carbons with different chemical environment we have in the structure. So each of these signals is a different carbon. So if we count them, we have 1, 2, 3, 4, 5, 6, 7, 8 signals. That means we have 8 different type of carbons in the structure. And if you compare it to the molecular formula, which has 10 carbon, we notice that there is not much of symmetry in this structure. So we have 8 carbons by looking at carbon NMR. Now let's look at these signals to see what the substituents look like or what kind of information we can get from these signals. So the first signal, it's a triplet with integration of 3 hydrogens. So we can think about having a CH3 group that is connected to CH2 group. So this CH3 group gives us integration of 3 hydrogens, and these 2 hydrogens, 2 plus 1, can make this one a triplet. So this is a triplet. Now if you look at the next signal, again we have 3 hydrogens as a doublet. So we can think about having a CH3 group next to the CH group. So CH3 group, integration of 3 hydrogens, and this hydrogen, 1 plus 1 is 2, makes this one a doublet right here. Now if you look at the molecular formula again, it's C10H14. So the ring can give us 6 carbons, and we have the remaining 4 right here. So we can connect these 2 groups that we figured out to form the substituent. So CH2, I can connect that to CH group. Okay, and there is one CH3 here. So this is my substituent, and I can connect it to the ring with this bond. So I'm gonna have okay, so this is the substituent that we figured out. Now let's assign each proton to each signal right here. So first we need to label all the hydrogens. I'm going to label all 5 aromatic hydrogens as A. This is B, C, D, and E. Now these 5 aromatic hydrogens that are directly connected to benzene ring, they all appear somewhere between 6.5 to 8.5 ppm. So they are right here. We cannot distinguish between these peaks. We already talked about it. These hydrogens almost have very similar chemical environments, so their signals appear on top of each other. So they are hydrogens A. Now this CH3 group, so we should see integration of 3 hydrogens, and there is 1 hydrogen on a neighboring carbon, so 1 plus 1, a doublet for this CH3 group, which is right here. Now for this CH3 group, again, we see a signal with integration of 3 hydrogens, and there are 2 hydrogens on a neighboring carbon, so 2 plus 1, a triplet for this one. So a triplet with integration of 3 should be this hydrogen. Now for hydrogens D, so it is connected to a CH3 group and CH group. So these protons are not chemically equivalent as this one. So we need to think about complex multiplicity here. So this CH3 group makes this a quartet, and this CH group makes it a doublet. So we should expect to see a doublet of quartet for this CH2 group here. However, the signals are not very clear here, but we can see integration of 2 hydrogens. So the only CH2 group in this structure is basically this group right here. So it can be hydrogens D. And the remaining peak is hydrogen E. So this hydrogen, again, it's connected to CH2 group and CH3 group. So that can make this a quartet, and this one can make this a triplet. So we expect to see a triplet of quartet for that, but we assign it as a multiplet because the multiplicity is not very clear here.